Hello students! In this video we continue our discussion of infinite series. Specifically, we're now going to look at the convergence and divergence of geometric series. First, let's recall that I mentioned something in an earlier video about partial sums, and I said that both telescoping series and geometric series are special series because they give us a good way to model the idea of the sequence of partial sums. And this is true. So let's then talk about the sequence of partial sums and how that affects the convergence and divergence of a geometric series. So recall what a geometric series looks like. A geometric series is a special series of a special pattern, and it's created by taking some real number a, making that our first term, and then sequentially after that, we are going to multiply each term afterwards by some value of r. This creates the infinite summation n equals 1 to infinity of a times r to the n minus 1, or a plus a times r plus a times r squared plus a times r to the third, etc., etc., etc. There's two things I want to recognize about this. The first thing I always like to keep in mind is that a geometric series has a value a, and that's a very important value, a right here, and that's when our n is 1. And then it also has another important value, r. R is the value that we multiply to get each term afterwards. So we take our first term and we multiply by r, and that gives me the second term. We take the second term and we multiply by r, and that gives me the third term, etc. So this pattern is very important in a geometric series. So that being said, let's talk about the convergence and divergence of a geometric series. The cool thing is we have a formula for a geometric series. Unlike in a telescoping series, every example was a little different, but a geometric series always fits a certain pattern. So this allows us to come up with a formula that we can use for every geometric series. So let's start by talking about the sequence of partial sums. Let's look at the kth partial sum of a geometric series. Now remember, what's the kth partial sum? So the kth partial sum is simply a truncated form of the infinite series. It would be a plus a times r plus a times r to the second plus dot dot dot, and let's think this through here. S sub k means the kth term in the series. So this is a sum that only goes to the kth term, right? And so if n is k, then that means I want to go, the kth term will then be a times r to the k minus 1, right? Because that's going to be my kth term in this series. Now our goal for determining convergence or divergence, if we're looking at partial sums, is to take the sequence of partial sums and specifically look at the limit as k goes to infinity of that kth partial sum. So we want to know what happens as k goes to infinity for this kth partial sum. That's the whole goal here. So let's start and let's look at two special cases. Let's first start by letting r be the value 1. So when r is 1, what does our kth partial sum look like? Well, when r is 1, that means I have a plus a times 1 plus a times 1 squared plus a times 1 to the third power plus all the way down until I have a times 1 to the k minus first power. And what does this tell? Well, let's continue to simplify, but we know that 1 to any power is always 1. 1 to the first is 1, 1 squared is 1, 1 cubed is 1, 1 to any power is 1. So really, what is this partial sum, this kth partial sum? S sub k is really consisting of a plus plus A plus all the way until I get over here to the end A. Now, how many A's are there? Well, we go back up. Let's just look. It's not too hard to decipher. We go from n being 1 to n being k. So that means I have a total of k A's right here. There are k terms here. And so if I have k A's, right, all added up, what does that give me? That tells me then that the kth partial sum is simply k times a, where a is some number not equal to 0. So when r is 1, it seems very easy to get the kth partial sum. So in the case when r is 1, the kth partial sum is k times a, where a is some number. And if I want to determine whether this kth partial sum converges or diverges, or the sequence of partial sums converge or diverge, I'll take the limit as k goes to infinity of this kth partial sum. And what is the value of infinity times some, this is what we're thinking, right? Infinity times some real number a. Well, what is that limit? Well, that limit is just infinity, isn't it? And if our kth partial sum goes to infinity, this sequence of partial sums goes to infinity, what does that tell us about our series? That tells us that our corresponding series does what? It diverges. So let me write down our series, n equals 1 to infinity, a r to the n minus 1. Specifically, in the case where r is 1, this here, this geometric series diverges. And it diverges because the sequence of partial sums associated to it also diverge. So now, I know this is a lot of math. It's getting me really excited though. You too, huh? It's a lot of math language, but the cool thing is, once we develop this pattern, then we simply use this pattern as our formula for all future geometric series. So it's important to kind of go through the pattern. All right, so let's see if we can't develop the bigger, broader case. So what do we do when r is not 1? Well, let's start by looking at the kth partial sum of the series again. So let's remember, we're looking at a geometric series, and the kth partial sum consists of the sum of the first k terms. So we're looking at when n is 1 and n is 2, all the way up to when n is k, and we're adding up these terms together. And so what was that expression again? Let's write that down. So if it's a geometric series, that first term is a, that second one is a times r, that third term is going to be a times r squared, all the way until we get here, which is going to be a times r to the k minus 1. All right, good. Okay, so now we're in the case where r does not equal 1. This makes it a little messier. Because if r doesn't equal 1, well, then my kth partial sum is a little more difficult to find. So let me do a little trick. You know all these wonderful little tricks we do sometimes in math. Let's take advantage of our knowledge of telescoping series, and let's do something interesting. So if r doesn't equal 1, let's take 1 minus r, and let's multiply s sub k by 1 minus r. What would that do? So let's take 1 minus r and let's multiply s sub k by 1 minus r. Remember, mathematicians at one time didn't have anything to do but play with math all day. So you can get creative and try new things. But let's take 1 minus r and multiply it times our kth partial sum. Now, we know how to FOIL, so let's FOIL out that right side, or distribute if you like. We're going to use our distributive property, right? So follow with me. We're going to take 1 times a, and then we're going to take 1 times a r, and then 1, right? And then we're also going to expand by using the distributive property and multiplying negative all the way through. Okay? And so what will we get? Let's expand this. We will get, so we have 1 minus r times s sub k equals, let's expand this out. So we're going to expand this out. We're going to get a plus AR, right? Plus AR squared. When I take 1 times A, 1 times AR, 1 times AR squared, I'm going to keep going, and I'm going to get AR to the K minus 1. So that's the first part. But then I'm going to add to it now those second distributions when I have the negative R times A. So then I have the negative RA, or if you like, negative AR squared, and then negative AR cubed, and then negative AR to the fourth. Do you see a pattern? I'm going to go all the way down, and then that last term is going to be negative AR to the K. Do you see that? Let me just put a little extra thing here. So R times this factor just off to the side, just because sometimes that algebra gets a little tricky here. So if I take R times A to the R, K minus 1, what do? We add exponents. When we put exponents together, we add them. So if I add these up, I have 1 plus K minus 1, and that's how I'm going to get K there, right? So that last term is AR to the K. So let's put this all together here on the right side then. That means I have 1 minus R times S sub K using algebra is, and what do we got going on over here? Kind of like our telescoping series, huh? Lots of things are canceling. And when things cancel, it smushes things up, doesn't it? Brings everything together. The positive AR and the negative AR cancels. The positive AR squared and the negative AR squared cancels. In fact, all of the terms cancel except the very outer two. The first term remains and the last term remains. And so that means on the right side, I have A minus AR to the K. So this gives me a really nice expression for the kth partial sum of any geometric series where R is not 1. A minus AR to the K over 1 minus R. Do you see how I just divided both sides of that last equation by 1 minus R? Do you also see why I kind of excluded that case of R equal 1? Because we can't have R being 1 in the denominator, right? So that's why we kind of had to take care of that R equals 1 first for this to work. So now if we're going to use the sequence of partial sums to give us the convergence or divergence of a general geometric series, I now take the limit as k goes to infinity of this kth partial sum. Are you getting like goosebumps? Isn't this pretty cool? Math is so awesome. All right, here we go. So now we're going to take the limit as k goes to infinity. Now remember, all right, a is a number, right? A is just a constant. A is a number, R is a number, and A is a number, right? So the only value here that gets affected as we go to infinity is this value right here, which is R to the K. This is the only thing that's getting affected as K goes to infinity. So what does that mean? Well, let's just take a look here. I'm just going to put it off to the side. R to the K. What happens as K goes to infinity? Let's just talk quickly about that. What happens as K goes to infinity? Well, it really depends on what R is, doesn't it? Because now we're back to those geometric sequences. What did we say about those geometric sequences? Do you remember? Like, let's just throw some numbers in, because sometimes when we put numbers in, it helps our brain recognize things a little better, like patterns and stuff. But look at these two expressions. R, remember R is a real number, right? So basically it can be an integer value or a fraction. But let's take a look at the fraction idea, right? So do you remember that if R was a small fraction, meaning a proper fraction, meaning if R was less than 1, what happened as K went to infinity? So as k goes to infinity, when r is less than 1, what happened to this? Do you guys remember? What did we say happened? It went to 0, didn't it? Because the bottom grew infinitely faster than the top. And so this whole limit went to 0. And what if we had a fraction which was more of an improper fraction, or in other words, was a fraction or a value where r was bigger than 1, then what happened? Well, now the top grew way faster than the bottom, and so we said in this case that limit was infinity. And so really, what happens with r to the k depends. It depends on two things. So if r is less than 1, that goes to 0. If r is greater than 1, that goes to infinity. So let's write out those two cases. So here we go. R less than 1, the limit as k goes to infinity of a minus a r to the k over 1 minus r. What did we just say? We just said that r to the k, when k is less than 1, that limit went to 0, right? That limit went to 0. And so what does that tell me? So that tells me this limit is just a minus a times 0, which is 0, over, I did a little goof there, over 1 minus r. In other words, that's just a, which is a real number, over 1 minus r, another real number. This is a finite number, isn't it? That means the sequence of partial sums converges, and it converges to a finite number. So the limit as k goes to infinity of the sequence of partial sums, I'll just quickly write that, it converges. And it converges to a finite number, and that finite number is a over 1 minus r. So that means that our geometric series follows the same case. So if r is less than 1, then a geometric series converges to a over 1 minus r. Oh my God, that's powerful. All right, let's do our last case. Hang on. Let's take r is greater than 1. So we're looking at the case where r is greater than 1. We're looking at our kth partial sum, a r to the k over 1 minus r. And we want to know what's happening to this. So let's take r to the k. And if r is greater than 1, I'll go back over here to my thought process, right? If r is greater than 1, that means I have a ratio inside bigger than 1. And that means the limit as k goes to infinity, this goes to infinity. Well, so then the top goes to infinity on a fraction, right? So I have infinity over some number, 1 minus r, whatever number. I have a constant down here. And so this whole ratio goes to infinity. And so what does that tell me? So when r is bigger than 1, what do we say about this limit then? This limit of partial sums does what? This limit diverges. And if the limit of partial sums diverges, then we know that our entire geometric series diverges. So anytime we have a geometric series where r is bigger than 1, that geometric series is going to diverge. So let's summarize everything we've done so far, and we'll summarize that into the theorem about convergence and divergence of a geometric series. Specifically, let's take any geometric series where a and r are real numbers, a is not equal to 0. Then that infinite geometric series will converge if the absolute value of r is less than 1. Moreover, it will converge to have the sum equal to a over 1 minus r. In other words, the sum of an infinite geometric series, as long as the absolute value of r is less than 1, is equal to a over 1 minus r. That same series will diverge if the absolute value of r is greater than or equal to 1. Notice the convergence and divergence of a geometric series doesn't depend on a at all, it just depends on the value of r. And so if you see this pattern of a geometric series, Without doing a whole lot of work, you can look at the value of r, determine what it is, and determine whether the series converges or diverges. Very quickly. We don't have to go through the whole step of finding partial sums. We just go and apply this theorem. So let's try that with a quick example here. Let me show you the power of the theorem. Now, we took a look at this example in a previous video, 3/4 plus 3/16 plus 3 over 64 plus 3 over 256. We saw that this was a geometric series, and the a value on this geometric series was 3/4, and the r value on this geometric series was 1/4. Remember, 1/4 was the value or the ratio that we multiply by each term to get the next term. So if a is 3/4 and r is 1/4, how can we tell if this series converges or diverges? Well, we're going to use our theorem. And which case are we in? So we're specifically looking at our r value. And because r is 1/4, that means we're on the case where the absolute value of r is less than 1. And therefore, right away, without doing any work, what can we say? We can say that the geometric series, right away, no work because we did all the work. That's the power of a theorem and a formula, right? So we can say that this geometric series does what? It converges. And more than that, we can actually find the sum of this infinite series. All right, so what is that sum? So the sum of the infinite series is given by a over 1 minus r. So our a value is 3/4. Our r value is 1/4. So we have that the sum of this series is going to be 3/4 over 1 minus 1/4, which is 3/4 over 3/4, which is just 1. And it converges to the sum of 1. This geometric series converges, and it converges to the sum of 1. That means that if I was to add 3/4 plus 3/16 plus 3 over 64 plus 3 over 256 forever and ever and ever, it would converge to the number 1. So that ends our theoretical discussion of convergence and divergence of a geometric series. In the next video, we're actually going to go ahead and take a look at more concrete examples. Students tend to like little concrete examples more, but the theory is so powerful that sometimes it's good to take a look at the theory too. All right, so in the next video, we'll take a look at some concrete examples of determining convergence and divergence of a geometric series.